Start the problems of test 4 review. We're going to start with problem 1. Problem 1 is an oscillatory motion problem. A lot of calculations needed for this problem. The spring in question number 1 is put into simple harmonic motion. If you hang a mass of 500 grams from this spring, what will the period of its motion be? If the equation of motion is given by the equation x is 0.3 sine omega t plus 0.5, what is the position, velocity, potential, kinetic, and total energy of the block at t equals to 1 second, and its maximum velocity and acceleration? So quite a bit of stuff to analyze. Well, first it says the spring is the same as the spring in question number 1. In question number 1 of the test 4 review, we had been given a certain question and we had been asked what is the spring constant of the spring. It turned out that the spring constant was 49 newtons per meter. So that's the only piece of information that we need from that problem. So we take that spring and we connect a mass from it. So you go this way, you stretch it, and you start analyzing the motion. The mass here, that's equal to 500 grams, which is 0.5 kilogram. So what are the equations that we're going to be relying on? Well, it's going to be x equals a sine omega t plus phi. Velocity is equal to a w cosine omega t plus phi. And a is equal to the, so each one is the derivative of the one before that. Velocity is the derivative of x, a w. And then this one is the derivative of that, so the w comes out again. Negative a w squared sine of wt plus phi. Okay? The other equations are the equations for the omega and the period and the frequency. It turns out omega is equal to square root of k over m. The period is equal to 2 pi over omega. The frequency is equal to omega over 2 pi. So actually frequency and period are inverse of each other. So if you do 2 pi over omega, you have 2 pi square root of m over k for the period. The more mass you have, the longer it will take for one period, one cycle. So the period t measures how many seconds it takes to go and come back to the same position it started with. The frequency is the opposite. It tells you, it's the inverse of this, 1 over 2 pi square root of k over m. The frequency tells you in 1 second how many times it goes back and forth. Okay? So let's begin by calculating the omega. So since we know k is 49, omega is equal to square root. Then we put k is equal to 49 here. The mass is half a kilogram, so we get square root of 98. So it's going to be close to 10. Okay, so 98. So it's going to be 9.899 radians per second. So this is called radial frequency, okay, or angular frequency, radial frequency, right? So that's the omega that goes in here. So now we have x is equal to 0.3 sine of 9.899 t plus 0.5. The 0.5 is the phase angle, meaning it's the initial conditions of the block. It describes the initial position, the initial velocity, the initial acceleration, and so on. So if I want to know what is the initial position, I put t equals to 0. In this section of the topics, you have to be in radian mode. So let's go to mode. Make sure we are in radians. Okay? So now we're going to take sine. Well, since this is 0, we have sine of 0.5. Multiply that by 0.3. We have the initial position of the block is going to be 0.143 meters. Okay? And if we wanted to know the initial velocity, we would also put into this one, we would put 0. So we would take AW cosine. What is my A? Well, my A is my 0.3 W cosine of, and then since we're going to put T0, you just have cosine 0.5. and then my W is my 9.899, right? 9.899, so we're going to have 0.3 times 9.899, so it's going to be 2.606 meters per second. So let's draw a little picture of what's happening here. It looks like the block has been stretched. If this is the equilibrium position, x equal to 0, the spring has been stretched by an amount of 14 centimeters, which is 0.143 meters. And the initial velocity, 2.606. So 2.606 meters per second, right? So that's the initial conditions of the block, right? And what's the most stretched that the block can be? The most stretched is actually the 0.3, right? So 0.3 is all the way somewhere here, 0.3, which is 30 centimeters, right? So it's headed to being in its most stretched position. We want to know its frequency and its period, right? Its frequency is equal to W divided by 2 pi. Okay, so we take the 9.899, we divide it by 2 pi. .575 cycles per second, which is the same thing as hertz, right? Now, if I invert that, the period is 1 over the frequency. So once you get the W, the other ones kind of fall through. 1 over the frequency, so we invert that. 0.6347 seconds. So what does that mean? Well, this means that it's going to go and then go all the way to its most compressed position, right? So if we draw this, we should draw this a little bit like this, right? So it's going to go all the way to most stretched position, come all the way to most compressed, go all the way here, all the way there, 0.63 seconds. X of t equals to 1 second. So we put in here, we put 1. So you have 0.3 sine of 9.8991 plus 0.5, right? So you take 9.899 plus 0.5. You take sine of that angle. Remember, you have to be always in radian mode here. Then you multiply that by 0.3. So that's going to give you negative 0.248 meters. Okay? So basically in 1 second, and that's actually the frequency was saying that. In 1 second, where's it going to end up? So it's going to, let's show this in a different color. It's going to go all the way here, come back, go here. Remember, that's 1 cycle, right? Go, come, and go. That's 0.6347 seconds, right? Now, in 1 second, where is it going to be? It's going to have gone, come back, come back, come back. Negative 0.24 brings it where? Oh, negative 0.24 brings it almost to the most compressed position, right? Because the most compressed position is what? Negative 0.3. Most stretched, 0.3. Most compressed, negative 0.3. So in 1 second, it will be at negative 0.248, almost the most compressed position. What is its velocity going to be? So then you take the velocity equation, right? 0.3 times 9.899 cosine of 9.899 plus 0.5. Okay? So let's do that. Negative 1.668 meters per second. That actually makes perfect sense because we know in 1 second it's gone, it's gone, it's gone. In 1 second it's here. Over here, where is it headed? It's actually headed to the left still, right? So its velocity should come out negative 1.668. Now the acceleration. Acceleration is going to be what? negative 0.3, remember the equation, omega squared. So the negative is already in the equation. Then we have to square this. Then we have to take sine of 9.899 plus 0.5. 24.319 meters per second squared.